Okay, here I am. We got any New York Giants fans here in Texas? Hey, hey. So here I am. I am a football coach. It's Tom Coughlin right there. Got a player right there. There's the referee, and there's the football. All right. So I come here from UC Santa Cruz, home of the mighty banana slugs. Watch out, Longhorns. In addition to football, we're pretty good at astronomy too. And I'm going to be talking today about imaging extrasolar planets. So before getting into actual extrasolar planets, I wanted to look at something a little bit closer. Can anybody recognize where this is? Raise your hands. Guesses. Sunny Santa Cruz, California? Got a guess here? Oh, man. It's Titan. It's Titan. Moon of Saturn. So, yeah, that went too easily. So, this isn't the Pacific Ocean right here. This is a hydrocarbon lake with some clouds and riverbeds going into it. There's a great diversity in the types of planets and moons even within our solar system. And so, what's really exciting about extrasolar planets is that there are even more things out there that we might be able to study. But we'll never be able to take an image like this of an extrasolar planet. So when we look at an extrasolar planet, it's so far away, it just looks like a point of light. And everything that we're ever going to learn about extrasolar planets comes from a single point of light. We can't resolve them into an image. So why bother studying extrasolar planets when we can take such amazing images within our own solar system? Question I ask myself constantly. So here, this is scale. The separation is obviously not to scale, but the scale of the planets themselves is correct with the sun. And so, if you look at this image of our solar system, the first thing you should notice is that we have four small things on the inside and four bigger things on the outside. And before extrasolar planets were discovered, we totally understood why this was. So there's a disk of dust and gas that starts when you're forming a new star and the planets around it. And then outside of a certain radius, it's a distance from the star. It's cold enough that ices can condense, and those can conglomerate and form little pieces of dust that get bigger and bigger and bigger, that form a core, and then gas accretes around it. So we expect to have big gas giants further out, and we expect to have smaller planets closer in. And then the first extrasolar planet was discovered in 1995, and it was a Jupiter that was right there. So everything that we thought we understood from our solar system, first exoplanet we find, it's completely wrong. So there are new types of exoplanets that we can discover, new types of planets that don't exist in our solar system, and of course it helps us put our own solar system in context. So why study extrasolar planetary systems when we can study our own in more detail? They tell us something about our own solar system's formation. They contain types of planets that are not found in our solar system. And a third one, which I haven't mentioned yet, is that you can study how they evolve. So most planets evolve on a longer timescale than an astronomer's life. So you can't just sit there and watch what happens as it forms and evolves and dies. So you have to look at planets of different ages, and you can do that with astronomy. Why am I personally excited about exoplanets? It's a really young field. The first exoplanet was discovered around the last time Texas won a Super Bowl. Ooh. Ooh. The first image of an exoplanet was 10 years ago. And then the first habitable exoplanet found by Kepler, like a rock in the habitable zone of a nearby star. We're going to hear more about habitable zones later. The 1,000th exoplanet, we found tons of these things now, was discovered in 2014. And now the very nearest star to the sun, we think that might have an exoplanet too. So they're everywhere. They're ubiquitous. And all of this has happened relatively recently. And there's so much that we can learn in a very short amount of time, this being a new field. So, of course, here's what we would like to understand when we're directly imaging exoplanets. Maybe we get a blurry image of the exoplanet. Maybe we can see a moon around it or something like that. But we can't even do that well. So here's a picture of Voyager looking back at the Earth. And it's just sort of a point all you can see here is that it's sort of a pale blue dot. This was Carl Sagan's famous image. And, you know, from the pale blue dot, maybe you can infer that it has oceans or a nitrogen atmosphere or something like that. So basically the strategy for imaging extrasolar planets is you see this point, this point of light, and you look at it at different colors, and you try to infer something about the properties of that exoplanet. That's the game that we're trying to play. The problem is that exoplanets are really faint compared to the stars that they're around. So this was an image that the National Geographic took to try to demonstrate the type of problem that we have. And I think, frankly, they couldn't even quite do it justice. But the idea is that it's like a firefly next to a searchlight 3,000 miles away. That's the actual technical problem that we need to solve if we're going to be able to image an exoplanet. And you could probably tell that that's a pretty bright firefly right there. So that's the type of problem that we're dealing with. Here's an actual extrasolar planet, or this is actually something that's a bit more massive than an extrasolar planet called a brown dwarf. And you can see where the problem is. This star is just a point of light, but it's so bright that it saturates all of the pixels on our digital camera. And then in the glare of all of that light is this planet right here. So for reference, this exoplanet is 7 arcseconds away. The way I think of arcseconds physically, if you hold up your thumb, this kind of works for everybody. Do it. Your arm's about, the arm to thumb ratio is about proportional for everybody. So that's about 1 degree on the sky. An arc minute is 1/60th of a degree, and an arc second is 1/60th of an arc minute. So we're talking about 1/600th of your thumb at arm's length. And then the thing that you're looking at is 5,000 times fainter. So that's sort of the first one that was discovered. The way that you actually do this is that you try to concentrate the light from the star as much as possible to bring the glare, into a peak and keep it away from the exoplanet. So this is actually, this is from a ground-based telescope right here, and then this is an image of the same planet taken from the Hubble Space Telescope. The Hubble Space Telescope takes extremely sharp images because it's in space, and that's what I'm going to get into in a second. So there are 2 things that limit our ability to image exoplanets. And the first one is the size of the telescope. So basically, the sharpest that you can make an image, and this is a quantum mechanical limit, is proportional to the wavelength of light divided by the diameter of the telescope. And so if you make a really, really big telescope, D, you can make a really, really, really sharp image. And throughout history, the thing that moves astronomy forward is making bigger and bigger telescopes. Galileo figured that out, that having a telescope was better than having an eye. And then throughout that, you build a bigger telescope, you can make bigger discoveries. So this is an artist's rendition of a telescope being built by the University of Texas, among others. This is the giant Magellan telescope. Each of these mirrors is 8.4 meters across. I would say it's about the size of this stage. And then there's 7 of them put together. So this is a really big mirror. It has to make incredibly sharp images too. So it's polished to the nearest nanometer to get to the types of precision that you need to see an exoplanet. And this is going to go in Chile, which is a great site for telescopes. Here is how they build those mirrors. So right now, 7 of these mirrors are being built. This is a rotating oven. You put tons and tons of glass in it, and you melt it, and then you allow the oven to rotate, and it basically, like if you rotated a cup of water, it turns into the shape of a parabola, which is exactly the right shape that you need to focus faraway starlight. So big rotating ovens, that's the trick. Here's a video inside that oven, and these are a whole bunch of blocks of glass. Let's see if the clicker works. Oops, I need to use the mouse for this, I guess. So the oven turns on and it slumps down and it melts, and that's really, really close to the shape that you need for a mirror. So I'll play it one more time. I'm not sure the answer to that. I know that it takes weeks to actually get it to the right shape and to cool. So melting it and making that shape is not the hard part, but you have to cool it very slowly so that cracks don't form when you do that. So in the oven, it takes weeks and weeks to do this, and then it takes even more months to let it cool down slowly so you don't get any cracks. So here's the idea. Everybody's trying to build bigger telescopes. At the University of California, Santa Cruz, this is a telescope that we built. It's currently the largest telescope in the world at 10 meters. There are actually 2 of these. And then here is that giant Magellan telescope I was telling you about, being built by the University of Texas, among others. And then here's California's answer to that, the 30-meter telescope. Yeah, bigger. That's right. Okay, so the size of the telescope, that's the most important thing. But it turns out if you just take the giant Magellan telescope, as big as that is, or the 30-meter telescope, and you point it at a star, it actually doesn't take sharper images than your backyard telescope. So that's very disappointing. And the reason why is because of turbulence in the Earth's atmosphere. So you're all used to seeing this. If you're driving down a highway, down a hot road, you might see sort of the shimmering along the roadside. And that's actually turbulence. It's basically like hot air getting convected around, and it distorts the image a little bit. So I have a video of this too, and I would ask you to ignore the turkey being dropped into the turkey fryer and look at the fence behind it. So if you look at the heat coming out of this and ignore the turkey, you can see the fence behind it, and it's moving around. So imagine that one of those points in the fence is the star you're looking at. It's moving around like this, and that's going to make it really hard to see the thing that's a million times fainter right next to it, right? So that's what atmospheric turbulence is doing. So here's the same sort of, this is the same sort of a video, but now I'm looking through a telescope at a star. And you'll see the same thing where the star is bouncing around, bouncing around. The star itself is actually tiny, but it's bouncing around so fast on the sky, it makes this blurred out image. And then partway through the image, I'm going to turn on what's called adaptive optics, which is the secret for how big telescopes can make really sharp images. So you'll see the blurriness going around, and then you'll see it whoop, shrink down. There it goes. So in this case, because this projector cannot do a 1,000,000 to 1 contrast, I'm showing you a star and a slightly fainter star next to it. But that's the idea, is that if you didn't have adaptive optics, you would have this huge circle of a star, and you'd never see the faint planet in there. But when you turn on the adaptive optics, it basically concentrates all the light of the star and keeps it away from the planet. It also makes the planet brighter because it's concentrating the light of the planet. So this is the trick. Okay, here's how it works. So light is coming from a star, which optically you can think of as being infinitely far away. And so the light expands as a circle from the star, and by the time it gets to Earth, you're looking at just a tiny little fraction of that circle, and it looks like a little flat line. So we get what's called plane waves coming from the star. And they've gone hundreds and hundreds of light years, and they're perfect plane waves. And then they hit, in that last second, they hit the Earth's atmosphere, and they go through that turbulence we've been talking about, and they get all distorted. So that's too bad. So if I do that, and I go through the optical system of the telescope, I end up with this distorted wave at the bottom, and that's the distorted wave that makes that faint, blurry planet right there that we don't want. Okay, so now I'm going to add on the telescope's adaptive optics system. So I have this turbulent wave going through, goes through, and the trick is that we put a deformable mirror on the back of our telescope. And that deformable mirror takes the exact shape that the atmosphere put into that wave to cancel out the turbulence in the atmosphere. And the idea is that we should get a flat plane wave coming back out of there, and the flat plane wave will make that perfect image that we're after. So the way this happens, the turbulent wave goes in, bounces off the deformable mirror, and then it goes off of this beam splitter. We send the infrared light to the science camera. That's where we detect the planets, is an infrared light. And we send the visible light to something called a wavefront sensor. The wavefront sensor basically measures the shape right here. And the wavefront sensor goes through this computer that in real time will measure that wave, tell the deformable mirror what to do, and correct the wave as it's coming. And it has to do this over 1,000 times per second in order to make these sharp images. So we're basically taking this starlight 1,000 times per second. We're measuring the shape of the starlight and quickly moving around our deformable mirror to correct it and make these perfect images over here. Okay, so now I'm going to show you what this looks like on an astronomical detector. So what I'm about to show you is a star, and I've corrected it as well as I possibly can. And you know, there's some detector artifacts. You can ignore those. This stuff's hard, but we've concentrated the light as much as we can. And let me know if you see anything. So the other thing that this does is it makes perfect. Oh, some people see something. What do you see? A planet. All right, good. So what happens is the adaptive optics keeps. I'm gonna show it one more time. So the adaptive optics keeps the telescope image of the star exactly perfect, and then that allows you to see something faint around it. And I believe people are pointing at that right there. I'm not sure. There may be more than one. Okay, so now the telescope has done all the work that it needs to do, and now it's the job of the astronomer to do a whole lot of math and try as best as possible to remove that starlight in post-processing. So that's going to be the next video. All right, now it should be easy to see, right? There's a planet there. There's one there. There's one there. If you're a professional, you'll notice that one there. Okay, I'm gonna help you out now and just sort of skim through it so it'll move a little faster. It'll be easier to see. So there you go. So each of these planets, by the way, is over 100,000 times fainter than the star. That separation right here is about a half of an arc second. So before I was showing you 7 arc seconds, 5,000 times fainter. That's what we used to be able to do in astronomy. Now we're doing 100,000 times fainter, even 1,000,000 times fainter at less than 1 arc second away. So that's where we are right now. And then I'll leave you with the final image when you rotate all of these and stack them together. Thank you.
Q&A. All right, we'll take some questions for our speaker. The idea is that I will call on you. You can ask your question. One of us will hopefully remember to repeat the question, and then you'll give your answer. Let's start here up front.
Sure, excellent. Great. I just got something that came into my, I get a subscription to Instructor.
Okay.
I talked about seeing, possibly detecting in this video, exoplanets in your backyard. And the equipment they were talking about using was not particularly large lenses. I think they're using the wobble method in order to take multiple images and then see the star moves. What's your thoughts on that?
Yeah, so they're different methods of detecting exoplanets, and I do think some of them you can do with pretty small telescopes. This particular one requires the biggest telescope that you can get, and that's because you're trying to spatially separate the planet from the star. The reason to do this is because then you can take images at different wavelengths and study what the object is made of. But there are other techniques. I think maybe the one you're thinking of is called the transiting technique, and what you do there is you have a star, and then the planet passes in front of the star, just like Venus passes in front of the sun. And you stare at the light of the star, and it gets a little bit fainter, maybe 1% fainter. And so with a really good setup and probably a pretty good site, maybe not downtown Austin, yeah, you'd be able to see the star get fainter by 1%. And from that, you would be able to infer how big the planet is.
All right, how about another question? All right, up top.
Okay, the question is, what does a deformable mirror look like? And the answer is that there are a whole bunch of different ways of doing this. This is like an active technology. It's a big industry for a variety of different subjects besides astronomy. So the ones that made that image are like particularly crazy. They're like this big. They're the secondary mirror of the telescope. So they're about 1 meter across. They're 2 millimeters thick, that's very scary, by the way. You've got a little piece of glass that's 2 millimeters by 1 meter. And then it's got 676 magnetic actuators behind it, pushing and pulling on magnets glued to the back of the mirror. And that's the one that made this particular image. There are other ones that are smaller. They can be as small as this big, and they're made by silicon lithography methods, for example. But generally, the idea is that you have little actuators pushing on the back of a mirror, pushing and pulling, and that's how you control it.
All right. How about right here up front?
So the method you mentioned blocks out the light of the star to find the planet. Theoretically, is it also possible to block out the light of the planet itself to find, let's say, a moon or something? And if so, has it been done?
Yeah, so the question is, you can block out the light of the star to see the planet. Can you also block out the light of the planet to see the moon? And so far, that has not happened. We have never seen an exomoon. There was actually a paper maybe 2 weeks ago about a possible exomoon, and that was discovered using a different method, so you can't actually see that one. And it's still a candidate, too. In general, the star is really, really, really bright, and the planet and the moon contrast isn't quite as bad. So you wouldn't need to block out the planet light to see the moon around it. But it's still beyond what we can do right now. Actually, I think what's sort of interesting is that a lot of times when astronomers think about moons, they think about like a moon of Jupiter. So Ganymede is really small compared to Jupiter. Our moon is not that small compared to the Earth. And I think if you were looking at Earth as an exo-astronomer, you'd probably just think it's a binary planet, right? So there are all sorts of different types of moons like that. And we're not quite at the point where we can do that yet.
All right, maybe one more question in the back.
The star is HR 8799. HR 8799.
We don't always have the sexiest names in astronomy.
I like it.
All right, we love when we have remote speakers come and speak with us at AoT ATX, so let's give a big round of applause to our speaker again.